Swayam Prabha. Digital India. Educated India.
So I noticed that this NP completeness has shaken people. Some anxiety, fear, curiosity, and some people feeling, really, is it really that hard? What about the following algorithm for traveling salesman problem, and so on and so forth. Okay, so which is nice. So the theory of NP completeness is somewhat subtle. It has various consequences, but modulo that, all these reductions is something easy, something which we always do as algorithm designers, use as an algorithm for another problem as a subroutine to solve another problem, right? This is something we always do, and that's what reductions are, right? So if you have an algorithm for click problem, I will design an algorithm for an independence set problem using that as a subroutine. So this is something we always do, and that's what reductions are about. But reductions are no means easy. If I have to show my current problem is NP hard, what is the problem I choose from, and what sort of gadgets do I construct? They are not easy. They are pretty hard. Whatever I did, for example, yesterday from vertex cover to Hamiltonian cycle is quite an involved reduction. I will not ask in an exam. I will not even ask it in a problem sheet. Okay, it requires certain experience to appreciate that. However, all the problems we have asked in the problem sheet are accessible. They all require 10-15 minutes of thinking if you understand the concept. So my first advice is just go and dirty your finger in trying to solve these problems, because they will complete your understanding of these problems, and they are accessible, except perhaps for one problem. It says this 3-dimensional matching, the last problem with the star. If you don't, it may take a few days. If you want to try, don't bother. But the rest of the problems are just help you round up the understanding. So my first suggestion is to just go and dirty your hands on the problem. They are accessible. As I said, NP complete reductions are in general hard, but I am doing the hard part. Okay, so in the class I am going to do the hard reductions. The problem sheets problems are all not that hard. Okay, the other feeling I had when several people discussed, oh, why not do this, why not do that kind of things, is that when you want to design algorithms, first thing you need to do is think complete, general, right? So first thing you have to do is to think in terms of complete general algorithm. Okay, so for example, let me just give you an example. This is something I always do. So let's say you have a list of n numbers. I want to find the maximum. I have a list of n numbers. I want to find the maximum of a given list of n numbers. Can you give me an algorithm? Simple problem. Yeah. I have a list of n numbers, and the goal is to find the maximum among them. Simple problem. Probably the first algorithm you would have seen in your algorithm course. Give me an algorithm for this. Okay. Okay, so that's a good start. It's still not a complete algorithm, right? So can you convert that into a program? Right? Take the first element as the maximum. Let's say I have A1, A2, AN, and you're going to say let the first element be a temporary maximum. So it's given in an array, let's say. Then so compare with A2. So if A2 is greater than A1 or max, or what do I want? Max. Okay. Then max is converted into A2. And then I am going to compare what? A3 with max. How many lines will you have this to? Put it in the for loop. So that's exactly what I am looking for. Okay. So first thing what I want you to do is think general. If I give you 15 numbers and I tell you give me a maximum, I know second standard students will do it. I don't need computer science to do that. But I am asking you to abstract out the steps. So, first of all, general, abstract, complete algorithm, right? I mean, this is something I was watching or in discussion. I want to do coloring of a graph and say, madam, take the maximum degree, okay, and then what, right? You have to give me I mean, so for example, can somebody tell me the Ford-Fulkerson max flow algorithm in 3 lines? I don't need a for loop, nothing. Just give me in 3 lines or 4 lines Ford-Fulkerson max flow algorithm, which you saw in about 4 or 5 lectures last week. So what is ST path? What is here? So your given input is an ST graph with ST capacities, edges. What do you do? What is the first step? Residual graph is for some flow only. So what is it? So start with the 0 flow on the edges. It satisfies all the constraints. Construct the residual network. Find an ST path in the residual network. Find a critical edge in that residual network for that flow. Augment the flow using that critical edge. You have a new flow. Compute the new residual network. Repeat until there is no ST path. Right? General, abstract, complete algorithm. Of course, I didn't tell you the details, implementation, all that will come into picture. So, if you have to, first of all, let's say you want to give an algorithm for a traveling salesman problem. Give me an algorithm. So it has to be like this. Oh, maybe start with the closest vertex, and then from there go to the next closest vertex, and repeat and come back to one. Okay, that's an algorithm. So first thing is, because what I have realized by discussions, the problem is not with NP completeness. The problem is here, that you are not thinking in terms of general, abstract, complete algorithm to start with. That is the first thing, right? And this has multiple levels. I am not saying that you have to break it up into complete implementation. That's the next level. But at least at a high level, you should have what the algorithm is doing. And if you see your problem sheet, there are there is a greedy algorithm for finding a minimum dominating set. 4-line algorithm, right? That's a complete specification which says find the highest degree, delete that vertex and its neighbors, continue until there are no vertices. The second important thing which we often ignore is correctness, right? Why does the max flow algorithm at the end gives you a max flow? You need an argument, you need a proof for it, and the proof is based on max flow min-cut theorem, right? Max flow min-cut theorem says that, oh, the flow is always bounded by a cut, but when I stop, I can give you a cut where the flow is equal to that, so I cannot improve anymore. So what I have is a max flow. Similarly, there is a proof for why Dijkstra's algorithm give you the shortest path. Similarly, there is a proof for why Prim's algorithm, Kruskal's algorithm give you a minimum spanning tree, right? Otherwise, it's just a heuristic. You can just say, okay, let's run DFS and pick this and color this and all that is fine. That's just a heuristic until you finish your correctness of the algorithm, right? So often the problem which we find, NP complete, for which I am just saying that brute force exponential algorithm is there, you can always come up with some heuristic. You might say, oh, why don't do this, why not do this, and it will come back. But in fact, there are at least 2-3 examples we have in the problem sheet where we argue that those algorithms do not produce the optimum. You have to come up with examples for it. They tell you that those algorithms are not correct in the sense that they don't give you what they are supposed to do. They don't give you the optimum, right? So correctness is important. And then the third thing is the analysis, right? Running time analysis. How much time the algorithm takes, right? So the last week experience is all about all of this for some simple problems, and now we are getting into more complicated problems. So all of these are becoming a tad more difficult. Okay, so So this I just wanted to convey this after getting some discussions, feedback about trying to understand what the difficulties are. Okay, because for example, when you see Prim's minimum spanning tree algorithm, you will take a graph and let's do this. Let's take the smallest weight edge and so on and so forth, and you'll get a spanning tree. But that's not the description of an algorithm. And why does it actually give you a minimum spanning tree? You need to argue correctness. And often in greedy algorithms do not produce optimum solution. Minimum spanning tree or shortest paths are one of the very few examples where actually greedy algorithms give you the optimum solution. Okay. So, and next week, or no, actually later this week, from tomorrow onwards, we are actually going to see some approximation algorithms, and where we will produce not optimum but something close to optimum, but everything can be mathematically argued. It's not just let's do this and we get some solution and I'll be happy with that solution. No, we will sit and argue about the solution, we'll sit and argue about the running time and all that kind of stuff. Okay, good. With that sermon, let me just go back to concrete examples of NP completeness. So, yesterday we showed that Hamiltonian cycle problem is NP hard by a reduction from vertex cover. Okay. So, today I am going to do one more reduction for the same problem, for the directed version of the problem. They both are very similar. So, let's so what the reduction I am going to do is from 3 sat to directed Hamiltonian cycle problem. Right. So, what is the problem I am interested in? Directed Hamiltonian cycle problem. Given a directed graph, it may have even multi edges, both direction. I want to know whether does it have a cycle that visits a directed cycle that visits every vertex exactly once. Okay, so that, and the fact that it is in NP is easy to see because the certificate or the proof would be a Hamiltonian cycle, and you can verify that these adjacent vertices are actually edges, they cover all vertices. Okay, you can verify in polynomial time. So, now what I want to show is that this is NP hard. How do I show some problem is NP hard? I will first take a known NP hard problem and reduce to it in polynomial time. Okay. So, the known NP hard problem I chose is 3 sat because it is what it is. Okay. So, what is the input to the 3 sat instance? So, I have to start with an input to the 3 sat instance and encode it as a directed graph problem where I want to find Hamiltonian cycle. Right? So, what is the input to a 3 sat instance? The Boolean satisfiability problem? A formula, a Boolean formula which is a conjunction of clauses, right. So, I am given a formula which is like this. Okay, on n variables. And what is the input to the directed Hamiltonian cycle problem? Yep, a directed graph. A directed graph, right? I want to get a directed graph here. No weights, no capacities, nothing. I want to get a directed graph. What is the property I want? From the formula, I am going to get a graph with what kind of property? F is satisfiable if and only if G has a Hamiltonian cycle. Okay, so that's the goal. I want to construct such a graph. I want to keep the goal in mind, so then that will guide my construction. That will tell me how to do this construction. Okay, and it's not easy, not very difficult, not as difficult as the reduction we had yesterday. So it will be. But this also I want to illustrate the point that yesterday our reduction was from vertex cover. So any problem, whichever is convenience, in theory all are you can encode one from the other because they are all NP hard problem. So whatever You think more natural, that's convenient, you can. And so we saw a reduction from vertex cover yesterday. I'm going to give a reduction from 3 sat. Okay. Right. So this reduction now is going to have okay, what is, again, let's give some intuition, right? So no, let me just complete the construction. So the graph is going to have n different paths. So these paths are of big length. Because there are n variables, I'm drawing n different paths, okay, and I will also draw edges in both directions. Okay, so these edges are also in both directions. There is an S and there is a T, and S is adjacent to both endpoints of all these paths, and this is T is also adjacent to, no, S is adjacent to only the endpoint of the first path. Sorry, T, I'm going to draw an H, and T is adjacent to this, and these endpoints are adjacent to, okay, both these next endpoints. So this is going to correspond to my variable x1, this is going to correspond to my variable x2, and this is going to correspond to my xn. Okay. For now, I haven't even, so what is my goal? I am given a formula, I am to construct a graph. So I look at my variables, there are n variables, I am going to draw these n paths going in both directions. Okay. These paths are of big length, the length is about 3m plus 3 or something like that. We will see why. So for now, does this graph have a Hamiltonian cycle? Look at this graph and tell me whether it has a Hamiltonian cycle. If the graph is not clear, ask me. Okay, let me draw the graph again. So start with S, and here is this long path of length 3m plus 3 corresponding to x1, another long path corresponding to x2. These paths are both sides. Okay. And then there is a T. S is adjacent to these two endpoints. T is adjacent to these two endpoints, and each of these endpoints is adjacent to both the next guys. Okay. Okay, so that's my graph. I just looked at the variables. I haven't even looked at the clauses yet. Just looking at n variables, there are m clauses. So I looked at n and m, and I have drawn this graph. Does this graph have a Hamiltonian cycle? Yes. Okay, give me the Hamiltonian cycle. So I also have to draw this H. Yeah. So one Hamiltonian cycle would be start from S, go to this endpoint, completely visit this all the way, and then come back here, visit all the way, come back here all the way, and come to T and go back to S. Okay. Is that the only Hamiltonian cycle? There are many Hamiltonian cycles. Let's see how many Hamiltonian cycles are here. I mean, finding a Hamiltonian cycle is hard enough. Now you want me to count how many Hamiltonian cycles? Well, how many ways can you visit these vertices? two ways, right? And I have given you freedom from S, you can go here or here, okay? And similarly, once you finish this path, I have given you freedom to go here or here. And similarly, after you finish one, there are two ways to visit each of these paths. After you finish, you have two ways to visit this and so on, and come back to T and then go back to S. So how many Hamiltonian cycles are there? 2 power n, very good, right? Now, this 2 power n Hamiltonian cycles are going to correspond to my 2 power n assignments for the xi variables for the Boolean formula, right? Each xi takes a 0 or 1. So, my interpretation would be if xi takes 1 in a satisfying assignment, remember our goal is this, right? I want to show that f is satisfiable means what? There is some assignment to the xi's that will simultaneously satisfy all the clauses, means I should be able to get a Hamiltonian cycle, and conversely if there is a Hamiltonian cycle I have to get a satisfying assignment, okay. So, these 2 power n Hamiltonian cycles are going to correspond to my 2 power n ways of setting the variables, okay. Now, this point you should ask me, well, this graph always has a Hamiltonian cycle, not one, lots of Hamiltonian cycles. So, how do we manage to prove this? What are we going to do? Right? I'm going to modify the graph, obviously, right? First of all, I have not even used my clauses. So far, I have used only the variables. So, I want to make, I'm going to include my clauses, how they look like, and based on that, I'm going to add some gadgets in a way that the Hamiltonian cycle may not exist at all. Because now when I add these new vertices, when will they exist? Only if this formula has a satisfying assignment, okay, that's the goal, right? I'm going step by step. So, there are 2 power n assignments corresponding to that, there are 2 power n satisfying assignments, but 2 power n Hamiltonian cycles. But now when I am going to incorporate in my construction the clauses, these Hamiltonian cycles may not exist, and they will exist only if there is a satisfying assignment for this formula. If and only if, okay. So, we will see why, okay. These are all for my, once I finish my class construction, you will see, right. But it's important that let's remember that these paths lengths are something large. I need at least 4m or something like that. Okay, so now what do? I have to now bring in my clauses, right? I have looked at only the variables. In fact, I have looked at n and m. There is nothing else I have looked at. So now let's say the first clause arrives. The first clause, let's say it is x1 or x2 bar or x7. Let's say it's 3-sat formula, right? What is my interest? So now I'm going to create a vertex for class C1. There's going to be new vertices coming in. Now I need to visit that also in my Hamiltonian cycle, right? Because the Hamiltonian cycle should visit every vertex. I'm going to bring in my class C1, and I want to say, when can I visit C1? Well, when is it satisfiable? If x1 is true or x2 is false or x7 is false, right? So, and I said if x1 is true means I'm going from left to right in the first path, x2 is false means I'm going right to left in the second path, and x7 is false means I'm going right to left in the seventh path, right? And now I want to say that in one of those 3 ways of visiting those variables, I can visit x1, okay? So, I'm going to now draw edges from C1. How do I draw edges? I go to my x1 and say x1 is positively appearing. So, when I go left to right, let us say this is vertex number 1 in the path, 2 in the path, 3 in the path, maybe 4 in the path. Then between 2 and 3, so I am going to draw this edge. So, in this path, the first 3 vertices correspond to my first clause, the next 3 vertices correspond to my second clause, next 3 vertices correspond to my third clause, and so on. That is why I want the length of the path to be at least 3m plus 3. Okay. Since it is C1 and since x1 is positive, I am going to traverse this path in left to right. So, if you traverse this path left to right, go ahead and include C1 between 2 and 3 and proceed. That is what I am going to do for my path C1, right. Now, when I come to, and we are not done with C1 edges yet, because I might visit X2 and then pick C1. So, between, so I'll have this, in this direction, it doesn't matter. Yeah, okay, let's say here are these 3 vertices, and X2, since X2 is negative, I am going to draw edges like this for C1 again, because this block corresponds to clause C1. And then I go to my X7, since X7 is also negative, I will take my that is the end of construction for C1. Okay. So, now next clause comes, I do something similar. So, similarly for C2, so there will be so many vertices here, there will be a vertex for C2, there will be a vertex for C3, there will be a vertex for Cm, but when I want to draw edges for Ci, I will take the ith block of this path, right. There are 3 vertices corresponding to the ith block. Depending on whether it is positive or negative, I will add an edge, I will go from left to right or right to left, and that is my construction. Okay. So, given a formula, a 3-sat formula, this is my entire directed graph. This is the encoding. Okay. So, I do not know the assignment, I do not know the satisfiability, but I have a goal in mind that somehow if there is a satisfiable assignment, I should be able to have a Hamiltonian cycle. If there is a Hamiltonian cycle, that should correspond to a satisfying assignment, and this is my construction. Okay. Now, things should fall in place. What is it we have to show? We have to show this, right. So, you are given a formula, I have constructed a graph, a directed graph, that is the goal, but I constructed in a way that this property is satisfied. Let me just give you a hand waving proof of this. I am not going to give a complete proof.